Hello, and welcome to Chapter 28, where we will discuss the evolution and distribution of galaxies. This chapter is going to explain how we learn about old galaxies, how galaxies grow, how they're distributed in our universe, and the challenges of dark matter. We're going to begin with how we observe distant galaxies. We have a lot of unanswered questions about our universe, and we pose some big picture questions about galaxies. These questions deal with how and when these galaxies form and what determines their shape. Is the shape determined at their birth or by the environment that they grow up in? To begin to even answer these questions, we first have to understand how we are even able to observe these galaxies. We cannot directly observe the changes in individual galaxies, because in a human's lifetime the galaxy barely changes at all. But we have one really useful tool in studying the evolution of galaxies, and that is considering the distance of galaxies. If a galaxy is 10 million light years away, we are observing light that is 10 million years old. So we are observing this galaxy in the past, so we can use this tool to our advantage. For example, the closest galaxy is 100,000 to a couple million light years away. Not much happens for the total shape of the galaxy during this time, so we can take that as the galaxy's present shape in present time. However, more distant galaxies are closer to 10 billion light years away. So that galaxy, the light that we are observing from it, is 10 billion years old. By observing these galaxies, we look further back during a time when the galaxies and the universe were a lot younger. So here you can see a sample of images that represent the most comprehensive compilation of galaxies in the early universe. This image here shows a cluster of galaxies from 3.5 billion years ago. So since we cannot observe the changes in individual galaxies, we can instead observe baby, toddler, and adult-aged galaxies. This way, we can piece together a picture of the evolution of galaxies. Fortunately for us, there is not a shortage of galaxies to study. To picture this, you can hold up your pinky at arm's length towards the sky. The part of the sky that's blocked by your fingernail, your pinky fingernail, contains about 1 million galaxies. And these galaxies are layered farther and farther back in space and time. So here we can see an image mosaic that was created using 16 years worth of data from the Hubble telescope. This image shows about 265,000 galaxies, and these galaxies stretch back 13.3 billion years ago. That is only 500 million years after the Big Bang. So looking back this way allows us to have a sort of cosmic time machine. These galactic changes over cosmic time is called evolution in astronomy. So when biologists use this word, it means the change in generations of organisms. However, when astronomers use this word, it refers to the changes in an individual galaxy over time. So astronomers are forced to observe at a distance. Therefore, electromagnetic radiation is a really good source of information for an astronomer. The distance to a galaxy is derived from its redshift. Its redshift is how much the lines in its spectrum, remember we talked about spectrum before, how much the lines in its spectrum are shifted to the red because of the expansion of the universe. So that is how we tell how distant a galaxy is. So the conversion of this redshift to distance depends on certain properties of the universe, including the value of the Hubble constant and how much mass it contains. So using all that information and some equations, astronomers are able to figure out how distant a galaxy is based on its redshift. So in addition to distance in this look-back time, studies of the Doppler shifts of a galaxy's spectral lines can tell us how fast the galaxy is actually rotating. And that is how we can determine the mass of the galaxy. Detailed analysis of these lines can also tell us the types of stars that inhabit a galaxy, and whether or not it contains a lot of matter. Astronomers also look at the fossil record of our own galaxy. This fossil record is the old stars within our galaxy. So we can actually learn a lot about the evolution of galaxies by studying the stars within that. So that is another way we gain some information. So for example, our own galaxy contains globular clusters with stars that are at least 13 billion years old, and some might even be older than that. So if we count the age of the Milky Way as the age of its oldest stars that reside in it, the Milky Way must have been born at least 13 billion years ago. So when we make computer models of how galaxies evolved in time, it actually tells us that the star formation in elliptical galaxies began less than 1 billion years or so after the universe started to expand. And after that, new stars continued to form for a couple billion years. However, suddenly star formation stopped. When we compare the distant elliptical galaxies with ones closer by, we find that ellipticals have not changed very much since the universe reached about half its current age. So observations of luminous or bright galaxies take us even further back in time. The spectra of some of these galaxies already contain lines of heavy elements. But these heavy elements were not present when the universe began. They had to be manufactured in the interior of stars. This means that when light from these galaxies was emitted, and we were able to observe it, an entire generation of stars had already been born, lived out their lives, and died. This was even before the universe was 1 billion years old. And it wasn't just a few stars in each galaxy that got started this way. Enough had to live and die to affect the overall composition of the galaxy in a way that we can actually measure it in the spectrum from really far away. So this conclusion is supported by observations of quasars. These are galaxies whose centers contain a supermassive black hole. We can measure the heavy elements in the gas near the black holes, and the composition of the gas that's emitted by their light 12.5 billion light years ago is still very similar to that of the sun. This means that a large portion of the gas surrounding the black holes must have already been cycled through stars during the first 1.3 billion years after the expansion of the universe began. So if we allow time for this cycling, then the first stars must have formed when the universe was only a few 100 million years old. So this image shows a very distant galaxy. The redshift that we were able to find indicates that it's 13.2 billion years old. And we are actually able to detect this galaxy by its really strong hydrogen emission. So the observations that all galaxies contain some old stars led astronomers to the hypothesis that galaxies were born fully formed near the time when the universe began its expansion. This hypothesis was similar to suggesting that human beings were born as adults and did not have to pass through time to develop from infancy through teens. If this hypothesis were correct, the most distant galaxies should have shapes and sizes very much like the galaxies we see nearby, and we do not see that. So the observation that all galaxies contain some old stars led astronomers to hypothesize that galaxies were born fully formed around the time when the universe began its expansion. This is equivalent to saying that human beings are born as adults, and they don't need to go through the stages of development from infancy through teens. So if this hypothesis were correct, the distant galaxies that we observe would have the same shapes and sizes like the galaxies we see nearby. And as we've already discussed, we don't see that. So thanks to the new generation of large and actually space-based telescopes, we now know that the pictures of galaxies evolving peacefully and in isolation from one another is actually completely wrong. We'll actually see later in this chapter that galaxies in the distant universe do not look like the Milky Way, and nearby galaxies and the story of their development is more complex and involves far more interaction with their neighbors than this previous hypothesis states. So why were astronomers so wrong? So up until the early 90s, the reason astronomers were wrong was because of the galaxies they were able to observe. In the early 90s, the most distant normal galaxy that they could observe emitted its light 8 billion years ago. and these galaxies that they were observing did evolve peacefully and slowly. However, since the 90s, powerful new telescopes have come online, and these telescopes can look back further than 8 billion years. So we have detailed views of thousands of galaxies that emitted their light a lot earlier, and some even emitted it earlier than 13 billion years ago. So one of these telescopes that came online is the Hubble Space Telescope, and it is really suited to studying the shapes of these old, faint galaxies. And to the surprise of astronomers, when they started to observe these distant galaxies, they did not fit the Hubble's classification scheme at all. The distant galaxies that were observed look very different from present-day galaxies. They don't have identifiable spiral arms, disks, or bulges. And it's not just their shapes that are different. The galaxies that are emitting light 11 billion light years or earlier are extremely blue. This indicates that they have a lot of young stars and that there's still star formation occurring in them at a higher rate than in nearby galaxies. So these observations also show that distant galaxies are systematically smaller on average than nearby galaxies. When we look at galaxies that emitted their light 11 to 12 billion years ago, we now believe we are actually seeing the seeds of elliptical galaxies. Over time, these smaller galaxies collided and merged to build up today's large galaxies. So here we can see this image that is the result of an 11-day-long observation with the Hubble Space Telescope, and it's of a tiny region in the sky. This is a region in the sky that only has a handful of Milky Way stars. So there are about 10,000 objects in this single image, and nearly all of them are galaxies. Each has tens or hundreds of billions of stars. We can see some pinwheel-shaped spiral galaxies, which are like the Milky Way. But we also see a large variety of peculiar-shaped galaxies that are actually in collision with companion galaxies. We can also see elliptical galaxies, which contain mostly old stars, and they appear as reddish blobs. Here we can see another image from the Hubble Space Telescope, and it's showing what is likely galaxies under construction in the early universe. All of these objects emitted their light about 11 billion years ago, and they are only about 2,000 light years across, which is much smaller than the Milky Way. The Milky Way has a diameter of 100,000 light years across. So these 18 objects are found in a region of only 2 million light years across, and are close enough together that they will probably collide and merge to build one or more normal galaxies. So the galaxy we see here emitted its light that we observe today when the universe was only about 500 million years old. When this light was emitted, the galaxy was tiny, only 850 light years across. That is 500 times smaller than the Milky Way. And its mass is only 40 million times the mass of the Sun. Star formation is going on in this galaxy that we are observing. So now we are going to discuss galaxies merging and active galactic nuclei. So astronomers have drawn the conclusion that collisions and mergers of galaxies play a crucial role in determining how galaxies acquired the shapes and sizes that we see today. This image here shows a dynamic view of two galaxies that are colliding. The stars themselves in this pair of galaxies actually will not be affected much by this cataclysmic event. And that's because there's a lot of space between stars. So a direct collision between two stars is very unlikely. However, the orbits of many of the stars will be changed as the two galaxies move through each other. And the change in these orbits can actually alter the appearance of the interacting galaxies. And here we can actually see a gallery of colliding galaxies. We can see great rings, huge tendrils of stars and gas, and other complex structures that form such cosmic collisions. And these are the strange shapes that signal to astronomers that colliding galaxies are happening in the image. So The process of galaxies colliding can take hundreds of millions of years. Thus, we best can study this with simulations on computers. So here we can see some computer simulations of galaxies colliding and merging, and this ends in a single galaxy being formed. So when two galaxies of the same size are involved in a collision, we call it a merger. It's the same term as you hear in the business world when two equal companies join forces. However, there are some galaxies that are bigger than other galaxies. And that, when they collide, or when that small galaxy is kind of swallowed by the bigger one, we call it galactic cannibalism. So here we can see some examples of this galactic cannibalism. So many of the large and peculiar galaxies that we observe owe their chaotic shapes to these past interactions. So slow collisions and mergers can even transform two or more spiral galaxies into a single elliptical galaxy. So when these galaxies collide, they change their shape. But that's not all that happens. If either galaxy contains interstellar matter, the collision compresses the gas and can trigger an increase in the rate at which the stars are being formed. We call this a starburst, and the galaxies in which we can observe this starburst they're called starburst galaxies. So in some galaxies, star formation is so intense that all available gas is exhausted in only a few million years. The burst of star formation is clearly only a temporary phenomenon. While the starburst is going on, however, the galaxy where it is taking place becomes much brighter, and it's much easier to detect at large distances. So when astronomers are looking back at galaxies that emitted their light 11 to 12 billion years ago, they find that these young galaxies often resemble closer starburst galaxies that are involved in mergers. They have multiple nuclei and peculiar shapes, and they are usually clumpier than normal galaxies today. They have a lot of intense knots and lumps of bright starlight. And they have higher rates of star formation than isolated galaxies, like we see in a starburst galaxy. So galaxy mergers in today's universe are actually rare. Only about 5% of nearby galaxies are currently involved in interactions. Interactions were much more common billions of years ago. So clearly interactions of galaxies have played a crucial role in their evolution. Just like merging, black holes inside of galaxies can also disturb and alter the evolution of the host galaxy. So if the black hole is surrounded by enough gas, some of the gas can fall back into the black hole, and it gets swept up in an accretion disk. Supermassive black holes and their accretion disks are violent and powerful in places. Some material gets sucked into the black hole, but even more gets shot out in huge jets. So these powerful jets can extend far outside the edge of the galaxy. So here we can see Centaurus A, and it has an active galactic nucleus that is powering two jets. So we can see it in blue and orange. So we can see it reach in opposite directions far outside the galaxy's stellar disk. This Centaurus is a distance of 13 million light years away, so it is actually one of the closest active galaxies we know. So now that we are aware of some of the complexities of the galaxies, we're going to look at how they're distributed in space. So taking pictures of the sky is similar to as if you were in a stadium photographing people. When you take pictures of people closer to you, they are bigger and only a couple fit into the picture. However, when you turn and take a picture of the opposite side of the stadium where the people are farther away, you fit more and more people into the photo the farther away you are. This is similar to how Hubble photographed the sky. The sky is too big to take one picture of, and taking individual shots of the sky would take longer than a human lifetime. So Hubble took 1,300 pictures. He found that, like our stadium, the numbers of galaxies increased with faintness, or with the distance. That's as we would expect if the density of galaxies is about the same at all distances from us. That's just like how more and more people fit into our stadium photo the farther away we took it. Also, he found out that the number of galaxies in each photo is about the same. So his findings are incredibly important for how we study the universe today. They indicate that the universe is isotropic, or it looks the same in all directions, and it's homogeneous. That means a large volume of space at any given redshift, or the distance, is similar to any other volume at that redshift. So that means it does not matter what section of the universe we observe, as long as it's big enough, any section will look the same as the other. This idea that Hubble introduced us to is called the cosmological principle. And this is the starting assumption for nearly all theories that describe the entire universe. Without this cosmological principle from Hubble, we could make no progress at all in studying the universe. So this is an essential principle in astronomy and astrophysics. So now let's discuss our local group. The Milky Way is a member of a small group of galaxies that we call the local group. This group is spread about 3 million light years and contains 60 or so members. There are 3 large spiral galaxies, including the Milky Way, 2 intermediate ellipticals, and a lot of dwarf ellipticals and irregular galaxies. New members of the local group are actually still being discovered. Many of the recent discoveries have been made possible by the new generation of wide field surveys, and these map the positions of millions of stars across most of the visible sky. By digging into this data from these surveys with computer programs, astronomers have turned up numerous tiny, faint dwarf galaxies that are there, but invisible to the eye, even in those deep telescopic images. So this image is a rough sketch showing where the brighter members of the local group are located. The average of the motions of all galaxies in the local group indicates that its mass is about 4 times 10 to the 12th mass of the Sun. So 4 times 10 to the 12th suns worth of mass. And at least half of this mass is contained in 2 giant spirals, which is the Andromeda Galaxy and the Milky Way Galaxy. And also we have to keep in mind something called dark matter, and a lot of the mass in this galaxy is in the form of dark matter. We'll talk about dark matter later. So there are groups of galaxies that are called galaxy clusters, and they are easy to spot even millions of light years away. And these clusters are described as poor or rich, depending on how many galaxies they contain. So rich clusters have thousands or even tens of thousands of galaxies, although a lot of these galaxies are faint and hard to detect. So here we can see the nearest rich cluster, and it is the Virgo cluster. This cluster is only 50 million light years away. So the largest cluster is called the Coma. It's 300 million light years away, and it is centered on 2 giant ellipticals, and they are as bright as about 400 billion suns each. That's incredibly large. So let's think about what this size truly is. The Coma cluster has about 10 to 20 or 30,000 galaxies. 1,000 galaxies. And each galaxy has billions and billions of stars. So that's 10 to 20 to 30,000 galaxies, each having billions and billions of stars. And if you were traveling at the speed of light, it would still take you more than 10 million years, which is longer than the history of the entire human species, just to cross this giant swarm of galaxies. So we are talking about huge, huge numbers here, and really, really big galaxy clusters. So here we can see this Coma cluster. So rich clusters, such as this one, usually have a high concentration of galaxies near the center. We can see giant elliptical galaxies in the central regions, but few, if any, spiral galaxies. The spirals that do exist generally occur on the outskirts of the clusters. So the largest universe mapping project to date is the Sloan Digital Sky Survey. Here we can see a plot of the distribution of galaxies, and it's mapped by this survey. To the surprise of astronomers, maps like this one show that clusters of galaxies are not arranged uniformly throughout the universe, but instead they're found in huge filamentary superclusters. These superclusters resemble an irregularly torn sheet of paper or a pancake in a shape. They can extend for hundreds of millions of light years in 2 dimensions, but they're only 10 to 20 million light years thick in the 3rd dimension. Detailed studies of some of these structures show that their masses are a few times 10 to the 16th of the mass of the Sun. That's 10,000 times more massive than the Milky Way galaxy. So separating these filaments and sheets are voids. They look like huge empty bubbles walled in by the great arcs of these galaxies. They have diameters of about 150 million light years, and the clusters of galaxies are concentrated along their walls. So that is how the galaxies are distributed in our universe. So now we're going to discuss something else that exists in our universe called dark matter. So in our universe, there's actually more dark matter than observable matter. So we cannot ignore the effect of this unseen material. So astronomers have looked for evidence of dark matter in the region of the Milky Way that lies within a few hundred light years of the Sun. Most of the stars here are restricted to a thin disk. It's possible to calculate how much the mass the disk must contain in order to keep the stars from wandering far above or below it. The total matter that must be in the disk is less than twice the amount of matter we can see. So to keep these stars where they are, there needs to be more mass than we can see. So that means no more than half of the mass in the region near the Sun can be dark matter. So here we can see an example of the kinds of observations astronomers are making for the Andromeda Galaxy. The observed rotation of spiral galaxies like Andromeda is usually seen in plots, which we call rotation curves, and they show velocity versus distance from the galaxy center. These plots suggest that the dark matter is found in a large halo surrounding the luminous or the visible parts of each galaxy. The radius of the halos around the Milky Way and Andromeda may be as large as 300,000 light years, which is a lot larger than the visible size of the galaxies themselves. So how do we observe this unseen matter? Albert Einstein showed in his theory of general relativity that the presence of mass actually bends the surrounding fabric of space-time. Light actually follows these bends. So very massive objects can bend light significantly. Dark matter is then revealed when it produces this effect. So that is one way we can observe it. The other way is in the light of X-rays. So here you can see the first method of observing dark matter. We can see numerous long, thin streaks, many of them blue. These are distorted and magnified images of even more distant background galaxies, gravitationally lensed by the enormous mass of intervening cluster. So these galaxies are distorted. So by carefully analyzing these images, astronomers can construct a map of the dark matter that dominates the mass of the cluster. And here we can see the second method of observing the dark matter. So just how galaxies have gas distributed between their stars, clusters of galaxies have gas distributed between their galaxies. And the particles in these huge reservoirs of gas are not sitting still. Rather, they're constantly moving, zooming around under the influence of the cluster's immense gravity, just like mini planets around a giant sun. As they move and bump against each other, the gas heats up hotter and hotter until the temperature reaches as high as 100 million Kelvin. It shines brightly at X-ray wavelengths. The more mass the cluster has, the faster the motions, the hotter the gas, and the brighter the X-rays. And that is how we are able to observe dark matter in this second method. Alright, so we keep discussing this dark matter. So we keep talking about dark matter, this unseen matter. But what is this matter made of? So the result of many experiments led us to the conclusion that the types of matter we are familiar with can only make up a tiny portion of dark matter. So another possibility is that the dark matter is composed of a new type of particle that we haven't seen yet. So researchers are now trying to detect that in laboratories here on Earth. So the kinds of particles that astronomers and physics have postulated generally fall into two main categories: hot or cold dark matter. The terms hot and cold don't refer to the temperature of the dark matter. It's referring to the average velocities of the particles. Say you're in a cold room, an air particle will move slower than if you're in a hot room. The air particles move faster. So that is why it's called hot and cold dark matter, not because of the temperature, but rather because of how quickly the particle is moving. So we are going to discuss the theory of hot dark matter first. So in the early universe, if the dark matter particles moved fast and farther compared to the lumps and bumps of the ordinary matter that we know eventually became galaxies and larger structures in our universe, those particles are hot dark matter. If this happened, smaller lumps and bumps would be smeared out by the particles' motions, meaning fewer small galaxies would get made. The theory of cold dark matter is if the dark matter particles moved slowly and covered only small distances compared to the sizes of the lumps in the early universe, it's cold dark matter. And their speeds are slow and their energy is slow, so even the smaller lumps of ordinary matter would survive to grow into small galaxies, so we would see more small galaxies than if there's hot dark matter. And so far, observations seem to side with cold dark matter. So now that we've covered dark matter, we're going to talk about the formation and evolution of galaxies and the structure of our universe. So this is more of a big picture. So we have observed quasars and galaxies that emitted their light when the universe was less than 1 billion years old. So we know that large condensations of matter had begun to form at least that early, if not earlier. So it seems likely that the supermassive black holes in the centers of the galaxies and the spherical distribution of ordinary matter around them formed at the same time. So this means that some of the first large concentrations of matter must have evolved into elliptical galaxies that we see in today's universe. So the more massive a galaxy is, the more massive its central black hole is. So somehow the black hole and the galaxy know enough about each other to match their growth rates. So there are two models postulated by astronomers for how the galaxies in the universe formed. So the first model is the top-down model. And this model asserts that the massive elliptical galaxies formed in a single rapid collapse of gas and dark matter. During this time, virtually all the gas was turned quickly into stars. And afterwards, the galaxies changed only slowly as the stars evolved. The second model is called the bottom-up model, and this model suggests that today's giant ellipticals were formed mostly through mergers of smaller galaxies that had already converted at least some of their gas into stars. So observations suggest that the giant elliptical galaxies that we see nearby formed from a combination of both of these models, with the most massive galaxies forming in the densest clusters, where both of these processes happened very early and quickly in the history of the universe. So the situation with spiral galaxies is apparently very different from this. The bulges of these galaxies formed early, just like the elliptical galaxies. However, the disks formed later. And remember that the stars in the disks of the Milky Way are younger than the stars in the bulge and the halo. And these disks still contain gas and dust. However, the rate of star formation in spirals today is about 10 times lower than it was 8 billion years ago. So the number of stars being formed drops as the gas is used up. So spirals seem to form mostly bottom up, but over a longer time than ellipticals and in a more complex way, with at least two distinct phases. So here you can see the growth of these spiral bulges. So astronomers are working really hard to measure and model the features of large-scale structures such as galaxies, elliptical and spiral. And they're trying to do this as accurately as possible. So far, a mixture of 5% normal atoms, the matter we know today, 27% cold dark matter, and 68% dark energy seems to be the best way to explain all the evidence currently available. So only 5% normal atoms. That's crazy to think about. So here we can see computer modeling, and this is computer modeling about how large-scale structures grow over time. This model considers dark matter, and the axis on the bottom here shows a time scale, starting with the Big Bang and working through present. So you can see how it forms a relatively smooth distribution, and we get the strings of galaxies. So we talked about a lot of information in this chapter. There's a lot of details to consider in discussing the formation of our universe. But let's discuss this big picture and what these details lead to. So in the beginning, we had lumps of matter. Each individual lump of matter expanded because the whole universe was expanding. However, as the universe continued to expand, the regions of higher density acquired more mass because they had a slightly larger than average gravitational force on the surrounding material. So if the inward pull of gravity was high enough, the denser regions stopped expanding. They then began to collapse into irregularly shaped blobs, and that is the word that astronomers use to describe this. And these elongated clumps existed throughout the early universe. They were oriented in different directions and collapsing at different rates. These clumps provided the framework for the large-scale filamentary and bubble-like structures that we see preserved in the universe today. The universe continued to build itself from the bottom up. With the clumps, smaller structures formed first. Then they merged to build larger ones. The first dense concentrations of matter that collapsed were the size of small dwarf galaxies, or globular clusters. Small galaxies and large star clusters first formed in the highest density regions of all. Some galaxy-to-galaxy collisions triggered massive bursts of star formation, or starbursts, and some of these led to the formation of black holes. So here we can see the formations of clusters of galaxies. This follows small clouds forming first, and then forming galaxies, and then clusters of galaxies. So that is chapter 28. Join us again for chapter 29 in the next lecture.